Welcome to the third video of the FP3 chapter, Hyperbolic Functions. I'm going to do the same thing that I did in the previous video and ask you to pause in certain places and give something a try for yourself. And again, we're going to start off with that to review the graphs. So if you've got time, pause the video now, try and sketch as many of these graphs as you can remember. When you're ready, play the video and I will sketch them on the screen here for you. So the Sinch curve has a gradient of about 1 in the middle there, and it comes up averaging out to about e to the x over 2. Similar on this side. Cosh comes out at 1 on both sides. Tanch kind of looks a little bit similar to Sinch in the middle there, but then it comes out this way and reaches an asymptote at y equals 1 and minus 1. Cosech, 1 over Sinch. If you do 1 divided by the Sinch curve, you get something that kind of looks a little bit like a reciprocal. Sech, however, is different because if you do 1 over cosh, 1 over 1 at the middle point, or the x equals 0 point is here, and then it comes down closer and closer to 0 on both sides, and it kind of looks like a little hill. Oh dear, that's not very good. And the coth, 1 over tanch, similar to the cosech, but the asymptote comes down at the same point as the tanch curve. So if I put those on there, the asymptote's here on the axes, here on the x-axis, here on the y-axis, but then here y equals 1, y equals minus 1, same as the tanch asymptotes horizontally. So I hope you were able to recreate some of those graphs, and we're going to move on now into the inverse hyperbolic functions. So this video is going to focus on the definition and also sketching inverse hyperbolic functions. The next video will look at the identities and move slowly into solving equations. So if you were to look at this and think about the inverse function without knowing anything about it, to find the graph of this function, perhaps you remember from previous work, we can reflect a function in the line y equals x. And if the inverse of a function exists, because remember it will not always exist, it needs to be 1 to 1 in order to exist, then we can get a graph of the inverse function by doing this reflection. So we're going to have a quick look at this with the Sinch function, and I'm going to pull up a little graphing app to show you. So you can see here in red we've got our Sinch curve, and I'm going to add on the y equals x line, and if you reflect that across you can probably see what's going to happen in your mind's eye. We're going to get the green curve here. It's going to start off very similar to the red bit here. It's going to come out at the 1 point, or gradient of 1 I mean, but instead of going up it's going to come across to the right. Obviously it does go up as well, but only a little. So that's the graph, and you could do that with all of the different functions and you could find the graph of the inverse functions, but that's not quite so helpful if we don't know what the function actually is. So of course we're going to do the algebra behind it to see what the function equals. Before we do that though, just a quick note on notation. The inverse hyperbolic functions, they again echo the trigonometric functions in how they can be written, and you can use a little minus 1, which if you remember your sine, you could do a minus 1 and do the inverse if you want to bring this over here. But you could also write that as arc sine. And that's a little more common if you do coding on a computer. It's a bit easier to write this than it is to put a -1 there. And we can do a similar thing with the hyperbolic functions. You can use the -1, that's fine. People will understand that this means the inverse sinh. But if you want to write it like this, then you use r instead of arc. R sinh y is the same as sinh -1. And of course, you know this is very different to 1 divided by sinh, which we call cosec. So r sinh is quite a common way to see this written. It's written like this in your formula booklet, and you will probably find it written like this in the exam as well. In some places, you would see arc sinh. They put a little c in here using the same 3 letters as they do here. This is a little more traditional. I don't know exactly where it comes from, but I have a feeling it's something to do with the trig functions being connected to arc length and the hyperbolic functions being connected to area, maybe area of a sector perhaps, I'm not 100% sure. But there is a reason why this used to be r and arc, and for the most part it still is, but you will sometimes see this written now as arc sinh. It means the same thing. And of course we've got the same for cosh, r cosh, and tanch, r tanch. So how do we know what these functions are actually equal to? Taking it off the graph would be a very difficult way. You don't normally work backwards from a graph to decide what the function is. We want to use algebra if we can, and we can do that using the exponential definitions of the hyperbolic functions and inverting them all. Going through, you know, exponentials invert to natural logarithms, so we're going to be using these. But I want to take you through one of the derivations so that you're clear on where this comes from. So we're going to start with r sinh x as our function. Now the derivation for r sinh, r cosh, and r tanch are all very similar, so I'll just do this one, but you can duplicate the derivation in a very, very similar way. To start us off then, what we're going to do is we're going to bring it onto the other side. And of course the inverse of r sinh is just taking you back to sinh. So if I write this as sinh y is equal to x, then I can apply the definition of sinh in terms of the exponentials on y instead of x. So I get e to the y minus e to the minus y divided by 2 is equal to x. And now basically what we're going to do is solve to find what is y in terms of x. So to do that I'm going to rearrange this, e to the y minus e to the minus y is equal to 2x. Then to get rid of that e to the minus y, I'm going to multiply everything by e to the y, which gives me e to the 2y minus 1 equal to 2x e to the y. And hopefully you can see what this is. This is a quadratic in e to the y. If I bring that onto the left, like this. So we can apply our formula for e to the y. And I'm sure you remember what this is. We've got minus b, so that gives us 2x, plus or minus the square root of b squared, which gives us 4x squared, minus 4 times a times c. A is 1, c is minus 1, so we get a plus 4. And all of that is divided by 2a, which in this case is just 2. Now I can tidy this up a little bit. I can pull a 4 out of that square root and make that 2 square root x squared plus 1, because I can factorize the 4, and then of course the square root of 4 is 2. Now if I divide by 2, I've got a lovely cancellation going on all over the place there, to give x plus or minus the square root of x squared plus 1. Now I'm going to deal with this plus minus here, because if you take a moment and think about this expression in the square root, I hope you can convince yourself fairly quickly that whatever this number is, if I square it and then add 1, and then square root it. Regardless of what I started with, that must be bigger than x. So if we know that this must be bigger than x, and all of this, remember, is equal to e to the y, and e to the y cannot be a negative number, then I can do away with my negative square root, and I can say e to the y must equal x plus the square root of x squared plus 1. Like that. But I still haven't got y, that's e to the y. To get y, I need to take logs of both sides. To get y is equal to the natural log of x plus the square root of x squared plus 1. And that is the definition of r sin x, because if you look back here, we've written y is equal to r sin x, and over here we've proven that y is also equal to the log of x plus the square root of x squared plus 1. Therefore, r sin x must equal that expression. There's a very simple reason why I wanted to show you that, beyond the obvious wanting you to understand where it comes from, and that's because you might be asked to do this yourself in an exam. You might have to prove it. However, if you're not asked to prove it, then you can use it without proof, because all of these are given to you in the formula booklet. You've got the 3 definitions in the formula booklet, which you can use without any problem. You don't need to show where they come from, unless the question is asking you to prove that they are true. So we've got, the little caveats here on the side, the limitations. What I meant to do. R sin any real number can go into there, because if you square any real number, you get a nice positive. But here, if you square something that is less than 1, you still have something less than 1. And when you subtract a 1, you're going to be trying to square root a negative number here, which we don't like doing. So here, for r cosh, x must be greater than or equal to 1. For r tan, the magnitude of x must be less than 1. Similar reasoning, because if you don't do this, if you have x is bigger than 1 or less than minus 1, you end up making a positive-negative combination in your fraction, which gives you a negative overall, and the log of a negative is not defined. So be careful with these limitations here. In terms of the graph, if you want to think about this, you've got the cosh graph. You've got to be a little bit careful. It comes out like this. And this point here is 1, 0. Sorry, 0, 1. And you know that we can't invert a function unless it's 1 to 1. And here this is not 1 to 1. So if we limit this here, say, okay, just from x is equal to 0 onwards, just take the positive x-axis. Then we get this in white. And that's a 1-to-1 function which we can invert. That's fine. And when you do that, obviously, you're limited here in terms of the range. Y is greater than or equal to 1. So when you invert that, that becomes your domain, which is why x must be greater than or equal to 1 in terms of the graph representation. So you've got reasoning there with the square root and the reasoning here with the graph, both telling you the same thing. Okay, enough of that. Let's use one in a quick example and then we will finish. So our example here, express r tan 1/3 as a natural logarithm. Like I said, if it's not asking you to prove these, you can use the formulas directly. So we can just stick that in there. Sorry. R tan 1/3 equal to half log 1 plus a third divided by 1 minus a third. And if you do 1 plus a third, you get 4 thirds. 1 minus a third, you get 2 thirds. And if you divide those, you get 2. Now that might seem a very simple example, but there is just another little thing here. Because it says express it as a natural logarithm, I would not leave this half here. If they want a natural logarithm, put it all inside the log. So just to finish this off, turn that into a square root of 2. And that is a single natural logarithm without any multiplier in front. There we go. Okay, if you've got the textbook, you can now practice using questions from exercise 1C. And in the next video, we will look at hyperbolic identities.